Are we here?
We're here.
All right, we are here.
Some more kitchen table astronomy with Hampshire College astronomer Dr. Salman Hameed, Mr. Universe, at your kitchen table in Amherst. A couple quick things. One, you went to go see Hassan Minhaj at the Williamstown Theater Festival on Friday. We tried to get him on our show, and we will be talking about some other things Williamstown Theater is doing, which is great. But how was Hassan Minhaj?
It was great, and it was Sunday. It was just yesterday, actually. And I would say, why? I mean, he should come to the show because there is now a South Asian connection. So I think
you can't play the South Asian card and get him on?
You should totally do that because you say you have a whole sort of like, thing about South Asia. So come on in. So no, it was really wonderful. It was a small audience. I love Williamstown Theater Festival because there's so many cool stuff that happens. So this was part of that. I think 2 years ago, or maybe it was last year, but there was this Close Encounters theme.
Oh
alien
yeah, I remember
theme, that. Sort of like it was.
They didn't want to come on our show either, remember?
It was this outdoor, sort of like, outdoor exhibit. I think it was 2 years ago. Anyway, that was so interesting, even though abductions didn't happen, but the belief in abductions definitely happens, and it was really cool. So I'm a, big fan, and so it was great to see in a small venue Hassan Minhaj over there.
Who's a comedian, of course. He was on The Daily Show. He had his own show. That was amazing. And we will have the Williamstown Theater Festival on later this week, so that's good. Another thing that's happening later this week, maybe, is a giant solar storm predicted for Thursday. Solar storms are what cause the northern lights to be seen, right?
Well, okay. So this is the bias that we have to correct. It's the northern and southern lights.
Okay, got it.
Okay, because we just go like, hey, who cares what's happening in the
Aurora Borealis? Does that cover it all?
That's exactly right. So Aurora Borealis, so that's when particles from the sun, like protons, for example, they get ejected, and people can tell if there is a lot of activity in the sun. So you can actually predict sometimes. And those charged particles, normally they don't come to the Earth because of our magnetic field. We are protected, but right around from the poles they enter, and then they interact with the atmosphere, particles in the atmosphere, and that's what produces these different colors. And in fact, there's different colors like green or red, and those different colors represent the different types of atoms that are in our atmosphere. And it happens all the time, but when there is a solar storm, you can actually see a lot more particles, and we can potentially see as south as here, but also down all the way down to New Mexico and Texas. And yeah, it is really cool. And I have seen them once in my life. I do want to go to Iceland or some other place to see it.
I saw them once in Turner's Falls.
A field trip to Iceland, by the way.
Yeah.
Fab 1413 Iceland.
Love it.
I'm sure Bjork would be happy. But I saw them from downtown Northampton during Northampton Film Festival, way back when there used to be a Northampton Film Festival, and they were red in color, and it was like around 8:30 or 9, and we just got up because there is no particular time per se. You can sort of like predict a little bit, but it's not like, after sunset, look at that time, or after. It's just, it could be at midnight or 3 in the morning and all of that stuff. So that's the one time I have seen. I would suggest there are some apps or some websites that track it, that can give you a little bit of warning, maybe, and try that. It's cool. And I know there have been reports over here, I think a couple of weeks ago or a couple of months ago, about some people seeing northern lights. It is really weird.
Yeah, and if you see weird green lights in the sky on Thursday or Friday, know that you're seeing the northern lights. When I saw them, I was like, what the hell is that?
And people think that it's clouds. It's like, because I remember during the film festival back in in Northampton, I was showing people, I was like, look, these are northern lights. Like, no, these are clouds. I'm like, no, actually, do you see stars all around? Oh yeah, okay. So yes, it will be just sort of like, wisps of different colors.
Yeah. And maybe, just maybe, this Thursday, Friday, you could see it.
I hope so. And call into FAB 413.
Yeah, if you see them, we definitely want to hear about it. Another thing that we won't see, but that astronomers have been seeing, that Einstein predicted over 100 years ago, are gravitational waves.
Right. So, this is an amazing story. So Einstein's general theory of relativity predicted. That's one way of thinking about gravity, is that it is the bending of space and time. So our universe is made up of 4 dimensions, 3 dimensions of space and 1 of time. And Einstein.
Which blows people's minds when they hear about that, but it's true.
Yes. And Einstein's theory suggested that if you have any object that has mass, would bend this space-time. And it is this bending that manifests itself. That's how we see it as gravity.
Now, you've explained this to me before in a way that has made it really concrete in my mind, where if you imagine space-time as a blanket, and you put a ping pong ball on the blanket, it's going to make a little dip in space-time. If you put a bowling ball on the blanket, it's going to make a massive dip in space-time. And that is how the fabric of space-time kind of works.
That's exactly right. And when objects move in there, and objects of course move, they create a little bit of ripples. But of course, a smaller object creates very little ripples. And so it was predicted that objects, especially that are big, they can lose energy that can be detectable as waves in space-time.
Like if you dropped a bowling ball on the blanket, it would make a ripple along the blanket, and we would be able to maybe perceive that ripple in the blanket.
And so that, so that was, in fact, there is a UMass connection, really important, because, and there was a Nobel Prize that was given in 1993 to two physicists, Taylor and Hulse. Taylor was a professor here at UMass and his graduate student. By the time they got the Nobel Prize, they were at Princeton, so it always writes down like, Princeton, but hey, come on!
Started at UMass Amherst.
And also they used Arecibo Observatory for their observations.
Which is the UMass-connected Mexican observatory, right?
No, this is the one in Puerto Rico.
Oh, Puerto Rico,
which
right.
is, rest in peace. It's no longer functioning. But what they discovered, they found these dead stars called neutron stars, and they can also be pulsing, and so they're called pulsars, but it's a similar thing. So they found sort of like binary pulsars, meaning to say one orbiting the other, which is okay. We know about these binary pulsars. What they discovered in there was that their orbit was slightly decaying. So this goes back to the thing that if you think in terms of Newton's laws, well, two objects are in motion, orbiting each other, and they should be orbiting forever. But not if they are losing some energy, which was shown, but how are they losing it? Where is that energy going? As gravitational waves. So it was their prediction that sure enough, and that's why they got the Nobel Prize, they could actually show the orbits decay, but they did not see gravitational waves directly. But this showed that they must be there. And then in 2015, I think that's where sort of like a lot of people remember big results from LIGO. This was this LIGO observatory, which was designed to detect gravitational waves.
Light interferometer, something or other, LIGO stands for,
Right, so it's a laser interferometer gravitational observatory, because this is a couple of kilometers wide. It has its arms, and there are these lasers, like very finely tuned lasers in there, and they can detect very tiny variations if there is something goes through it. And of course it's very, very hard to do, because you have to take out all other kinds of interference and want to make sure that this was through gravitational waves. There is another detector as well up in the northwest, and they detected for the first time gravitational waves which could be sort of like pointed to colliding black holes. And that was a stunning confirmation. Now there are colliding neutron stars, colliding black holes, because we know that when they collide, so you can imagine these very dense objects,
two bowling balls,
and when they are colliding, they are just producing this intense energy which is going out in gravitational waves, and this is what we detected. So it was a stunning confirmation of general theory of relativity predicted by, again, from Einstein's theory. So far, and now I think several dozen of these, or maybe 100 of these colliding black holes and neutron stars have been detected through gravitational waves. Well and good. But just last week or a couple of weeks ago, a new announcement came up, and that was about the fact that astronomers have found gravitational waves from a different method. And this is a different way of detecting gravitational waves, but also different types of gravitational waves. And this is what the astronomers that have been involved with this project, they call it sort of like the background hum of gravitational waves.
Because theoretically, the universe is so old, things have been colliding with each other forever, that there is this constant hum of gravitational waves rippling, because all sorts of ping pong balls and bowling balls and baseballs and softballs have been dropping in the fabric of space-time for, what is it, 4.8 billion years or something?
Go further back, 13.8 billion years. But here is the thing. So what astronomers expected, again, as we said, all kinds of objects, when they move, they should emit gravitational waves. But the waves could have different frequency, just like you have light or sound waves that have different frequencies. Okay, so all I'm doing it is different frequency in the way the sound is pushing, sort of like, the particles in there, and that's what's producing it. Same thing with light. You can have short frequency or high frequency, or short wavelength or high or large wavelengths. In the same way, you can have gravitational waves that can have short frequency. That's the kind that was detected by LIGO, or really long frequency gravitational waves. It's just where the peaks and crests are of a wave. But you would need a much bigger detector. So if it is on the scale of kilometers, LIGO would detect it. That's what it detected in terms of for the black hole collisions. But astronomers were like, but you can have these supermassive black holes. These are like, so the black hole collisions that were detected, those are like sun size, like 10 times, 100 times bigger than the sun in terms of mass. But we know that supermassive black holes exist in almost every large galaxy. Like the Milky Way, we have a supermassive black hole about 4 million times the mass of our sun, and that's on the smaller side. There are supermassive black holes at the centers of galaxies that are much bigger, and we know galaxies collide. So you can have two supermassive black holes in galaxies as well. We know that, and they potentially collide as well. So what kind of things, when they're moving, what kind of gravitational waves they would be producing, and it was expected that they would produce it on a much sort of like, longer wavelength or longer frequency, sort of like a higher, lower frequency. That's what they would have a background hum if you think about all the supermassive black holes doing that.
Yeah.
The problem was you needed a detector that is much bigger than LIGO. In fact, you needed a detector on the scale of tens or hundreds of light years. And so astronomers found a way to create that.
How?
Well, that's where it gets really interesting, because what astronomers did was, there are these millisecond pulsars. So we already talked about pulsars because of the binary, two dead stars, basically two neutron stars orbiting each other. So there is a whole family of these pulsars. These are, again, dead stars, but they're spinning really fast, and because they have high magnetic fields, they also send these pulses. Some of them can go over 100 times in a second. So here is a second, and these objects that are about the size of New York City have gone around about 100 times or more. So they are actually really good for measuring time. And in fact, they are the best timekeepers that are natural. And for a while, we actually humans here on Earth, used these millisecond pulsars as timers, because they would just give you very accurate time information that is sort of like, that is natural, and they would do that. So what astronomers did, and there are multiple arrays. In the US also, there is one pulsar timing array, but there are also in Europe, in India, in Australia, and in China. They were all had these different pulsar timing array, and they looked at these pulsars. So the US one looked at about 68 millisecond pulsars distributed over a few thousand light years across in the Milky Way galaxy. And then they looked at it over for 15 years. If their times with respect to each other have changed a little, and because they're very accurate, right? So they are they are going in milliseconds, sort of like, in terms of their pulses. And if there is a slight change, and because they are distributed across the galaxy, you can actually predict if a gravitational wave, if this disturbance in space-time has gone through, you can predict how each of the pulses from these different pulsars, of this array of pulsars, 68 pulsars, would change. So it's not just a change between one, it's the change across these 68 pulsars, and it would have to be predicted based upon if a wave have gone
It's
through.
like looking at a stadium. You see the wave happening over one part of the stadium, the wave comes all the way around, and they use those 68 pulsars to see these gravitational waves and found out what? That they are kind of constant? That they're there all the time?
That's exactly what they found was like, that's what they expect, sort of like, that there is this kind of waves, that is a background hum. So the example that one of the astronomers used, and I really liked it, that this is kind of like a background chorus. But then the ones that LIGO detected, which are much higher frequency, it's like a, sort of like, a chirp. So, thank you for my vocals here. So that's what it is. Now, I should have one or two points of caution. So, I mean, this is really cool. I mean, that we figured out how to use these millisecond pulsars, which, by the way, we should talk about at some point, because those are absolutely bonkers objects, because they are so fascinating. They are star exploded, like, supernova. You have this really dense, strange neutron star there, which is pulsing really fast, and some of these are in binary systems, so they get speeded up more, so they are pulsing like hundreds of times in a second, so they're crazy in itself. But we were like, okay, hey, let's use them as a timer to find out something even more amazing. So this story that we can use dead stars across the galaxy to create a large, in some sense, a telescope array, to figure out that there is this gravitational waves, a background there. So that's phenomenal. But two things of caution. One, the result looks pretty solid, because all of the all of the telescope arrays or pulsar timing arrays have seen a similar type of thing, but it's not 5 sigma. So 5 sigma is something that, in terms of errors, like, that 1 in a million times, roughly. Sort of like, that the chances, like, that could happen by chance. Usually astronomers use it 5 sigma, or physicists use it 5 sigma. This is about 4 sigma. So it's like pretty few, 10,000 or so.
Solid A minus.
It's pretty solid, like, So that is one thing, just to keep in mind, like, that the results are there, but it's pretty tight. Second thing is, I've been mentioning supermassive black holes as a potential cause. We actually don't know, because all we are seeing is this gravitational hum, or this background hum of gravitational waves. And it looks like, because we know supermassive black holes exist. In fact, one of the, the stuff around it was imaged. That was the big, the radio telescope image of supermassive black hole, the event horizon. That was one of the supermassive black holes. So we know that they exist. But is that what is causing this background hum or not? That is still a little unclear. It's likely. But before we go, I'll just leave a little bit of but maybe it could be something else. And two things that people suggest. One is that right after the Big Bang, after the universe started expanding, there was a phase, very, very beginning. There was a brief phase where the universe expanded like crazy. Okay, it's called inflation, and we can talk again about some of the
Bidenomics.
So, and it may be a sign of inflation that we may be detecting these gravitational waves. There are ideas like why it might be. Or, and now we are going into really Star Trek territory, there are these objects called cosmic strings, which are sort of like, very thin cracks in space-time. You can think about it that way, which, again, theoretically, they may exist, but there hasn't been any evidence for it. So some models suggest, that it might be these gravitational waves have been produced by cosmic strings. They're not ruled out by that. It might be. So that would bring in slightly newer physics. So we don't know. But now that we think we know how to detect this background hum, now you can go out over the next 10, 15, 20 years. This is basically opening up a new universe. You can go out and try to isolate what kind of objects are contributing to this background hum. So really cool, but if nothing else, just think about using amazingly strange dead stars across the galaxy to detect gravitational waves. I think that's cool.